Now let's say if we have an object hanging from a ceiling and we decide to apply a downward force to it. This object is under tensile stress. The tensile stress is force divided by area. Now, because this object is in equilibrium, if there's a downward force, there must be an upward force acting on the object. And that upward force and the downward force extends throughout the object. So whenever an object stretches, it is under tensile stress. Now, the tensile strain of the object is the change in the fractional length of the object. So let's say this is the original length, L0. Then when it stretches, it's going to become longer. And so this new length, or the change in length, that's delta L. So the tensile strain is going to be positive delta L divided by L0. And keep in mind, delta L is the change between the final length and the initial length. Now let's say if we have a column that rests on a horizontal surface. And if we apply a downward force on this column, then there's going to be an upward force acting on it too, which basically equates to the normal force exerted by the surface. Now, a portion of that normal force is going to be equal to the downward force that we apply to it. The normal force is going to be the sum of this force plus the weight of the object. But if we take out the weight of the object, then a portion of the normal force is going to be equal to that downward force. And those two forces causes compression. It causes the object to decrease in length. So this object is under compressive stress. So the compressive stress, it's still force divided by area. So in this case, we have a circular column, so the area is going to be pi r squared. Here's the original length of the column, and delta L is the change in length. So this time, delta L is negative because the length of the object decreased. So the compressive strain of the object is negative delta L divided by L initial. Now, you need to be familiar with the maximum stress that an object can have. So, for instance, let's use concrete as an example. The ultimate strength tells you the maximum stress that an object can have without breaking into two parts or breaking into pieces. For example, the maximum tensile strength of concrete is 2 times 10 to the 6 newtons per square meter. And the maximum compressive strength of concrete is 20 times 10 to the 6 newtons per square meters. So if you're dealing with the maximum tensile strength, that's going to be equal to the maximum force divided by the area. If you're dealing with the maximum compressive strength, that will also equal the maximum force over area. So when you hear the words tensile strength, compressive strength, it tells you the maximum stress that can be applied to material. So these values represents the maximum force over area. Now notice that concrete's compressive strength is stronger than its tensile strength. So what this means is that concrete is very difficult to compress. If you try to compress it, it's going to be strong in this direction. However, if you try to stretch concrete, let's say if you try to pull it apart, it's weaker in this direction. So it's a lot easier to pull apart concrete than to compress it. So concrete is very useful if you're trying to put weight on it. But if you're trying to stretch it, it's not as strong in that direction. Now, don't forget about this equation. When you're dealing with tensile stress or compressive stress, if you need to calculate the change in the length of the object, that is delta L, you can use this formula. Delta L is going to be 1 over E, where E is the elastic modulus or Young's modulus, times F over A. F is the force applied, A is the cross-sectional area, times the original length, L0. Now, Young's modulus, or the elastic modulus, you can look it up in a table. And it's important to know that the elastic modulus is the ratio between the stress applied and the strain of the object, or the fractional change in the length of the object. So this is another equation that is useful. So make sure to use the elastic modulus when dealing with an object under tensile stress or compressive stress. Now, what about if an object is under shear stress? So let's say if we have an object like a box or a book and we apply a force. The object is going to move in this direction. It's going to deform like this. And it turns out that there's another force acting on it. The force that you apply to the right, the ground is going to apply another force towards the left. And so it's going to deform like the shape that you see here. Now let's turn this into a 3D structure. So this is the cross-sectional area. That's A. And this is the original length. And this is delta L when dealing with shear stress. So we're going to have a very similar formula to the last example. Delta L is going to be 1 over G times F divided by A times L initial. Now this equation is very similar to the last example. The only difference is we have a G instead of E. E represented the elastic modulus, which is the ratio between stress and strain. In this example, G is the shear modulus, which is the ratio between shear stress and shear strain. So it's still stress over strain, but just with a different type of situation. Now, the shear stress is still force divided by area. And the shear strain is delta L in the horizontal direction divided by L0 in the vertical direction. So that's a little different. So keep this in mind. The shear stress that's acting on the object is the ratio between the force applied and the cross-sectional area. And the shear strain is simply delta L divided by L0. So G, the shear modulus, is going to be F divided by A, the stress, divided by the strain, delta L over L0. So let's review what we've learned. Let's say if you have an object with two forces pulling the object, causing it to increase in length. This object is under tensile stress. And whenever you have an object where the forces are decreasing the length of the object, this object is under compressive stress. It's being compressed into a shorter object. And whenever you apply a force